X-Force, va a estar hablando sobre payloads, binarios y demás yerbas. Dimitry, fuerte el aplauso.
Hear me? Can you guys hear me? Hola, Argentina. Thank you very much, Ekoparty. This has been a great team. Thank you. Here, the first time at Ekoparty. But today, the talk of the conversation is going to be about elves. Not the nice Christmas elves, but the very, very vicious and malicious elves that red teams use to help themselves. Who am I? My name is Dimitry. I work for IBM X-Force. You can find me at Twitter. I'm currently with research, doing offense and defense research, but previously mostly red team operation, malware work, Unix administration, app development, and so on and so forth. So hopefully we can kind of talk through different sides to help the red team win. Vamos. So agenda is we're going to take this talk from the red team perspective. Red team on Linux failed, miserable. We did this engagement a few months ago, I should say a year ago, and we were in an environment that essentially did not allow us to move very much. We'll talk more in details what that environment actually entails and how we overcame the deficiencies and were able to actually succeed in a way, but this talk is really from that perspective. Red team failing and then trying to achieve the dominance. But more specifically, the payload delivery failed, right? We could not bring a lot of things in. We could not establish that foothold and persistence. And essentially, everything sort of rolled down from there. The environment did not allow us to pivot in a lot of ways. We went back to a drawing board and started thinking what we can do about it, right? And so this evolution of how we overcame the challenges through various ways of payload delivery in Linux, that's what we're going to talk about. And then the idea that came through when we started looking at ways to overcome these challenges is how we can actually use ELF sections to help our cause. Kind of moved with that flow, we came up with a technique called ELF section docking. Obviously not by ourselves, we used a lot of open source ideas and some of the tools you're going to see here, but essentially the culmination of it, we were able to achieve our agenda. And not only that, but we also had a way to persist for the long haul. The detection was rendered useless for us, and so that was our goal. That was our immediate goal, right? But then analysis of the detection of the blue team, right, and how we can help them to achieve more introspection into what we did. So the evasion and then the detection of what we did and how the blue team actually got the tools to detect us. And then the last but not least is the ELFPack demo, right? The ELFPack is the structure, this factory that we've created to solve that cause. All right. First, why Linux? And why Linux malware? I can give you two reasons. The first reason is kind of dry statistical, is because it's prevalent in the cloud, right? If we are to work for our customers and if we were to achieve our dominance in the cloud, we should work with Linux. Now, CrowdStrike and Trend Micro provided some statistics into what Linux malware right now is. It used to be that, you know, there's a lot of ransomware that was on there. Right now, due to decentralization, we're moving to coin miners, right? And also the data that lives on Linux is important because you have databases running on it, you have middleware running on it. A bunch of banks run Linux in the cloud right now. And so for our cause, because we were doing such a work, it was important for us, right? But the real reason that we care about is that we have a hard truth reality. We are on Linux and we can't do anything with it, right? So that's our reason. This is the industry reason. So let's talk about the failures. Usually, and many of you probably are familiar, when the red team deploys, they have an objective, a goal to achieve, right? Whether to get to a customer data, maybe get some dominance on computing power, establish the foothold, and maybe pivot out into some very sensitive areas of the company. But the thing of it is, everything kind of starts with the first payload. You can deliver it via phishing, or you can do, whatever ways you end up being on the inside. This is not trivial in a lot of ways, right? So, speaking specifically of the Linux system, we had a scenario where we had a really large environment of Linux, but we had hardened hosts, a jump host that you need to get onto and then fan out to the system. And that presented a problem. The hosts were hardened. A lot of tools were removed from them, including, obviously, compilers. Interpreters were not there. Python was not there. So we couldn't drop executables. We got detected. If anybody works in the red team, they know that a cat only has maybe 3 lives. We lost 2 lives already by essentially not able to drop the payload on it, got detected, got a knock from the blue team, say, hey, what are you guys doing? All right, failure means going back to the drawing board. So executables were detected by static detection. We tried to pack it, did not go. After the fact, we've learned that they had both static and dynamic detection on the unwrap of the executable, so that's out of the window. We tried to bring frozen binaries. We needed to bring, for example, inpacket. That's a Python toolkit, and the whores are working with inpacket and frozen form. Especially with the absence of Python interpreter in the system was really a challenge. So we tried that. We got detected on temporary files on wrap. So when frozen binary runs, the payload gets dropped into temp directory. Done, right? And then the other challenge is that all that needs to be done with in memory, right? Because we do not want to use the temporary directory. And then we are going also against the, Richard talked about eBPF. This was exactly the scenario where we had to go against eBPF-based EDR. So all that was on that host that we needed to get through, because after that there is greener pastures, let's just say. So I'm going to kind of walk through this engagement as a series of thoughts, right? A failure, a cause, an effect, and then the result, and how we went through this. I think it will be beneficial to kind of walk through the chain of thought to getting to the solution. So naturally, we had limited set of tools ready for this engagement, right? We obviously could build more, but the timeline was not there. So strategically, from 30,000-foot overview, you can have payload delivery in 2 ways. You can either have a dynamic delivery, your standard, you have a stager that is very small, that doesn't do much, then possibly you go out on the network, connect to your C2, bring another stage, somehow launch it up, execute it, and on and on and on you go. Hopefully to the very end where the actual payload you need happens to be running on the system. Dynamic is about 70% of the time in our cases, right? Because you have this gap between what EDR knows on the system as a stage and what it knows as a final product, right? When things run. The static part is for very specific engagements, for very specific reasons, right? When we say, okay, dynamic fails, the loader is signaturable, right? It's everybody kind of knows whether it's a interpreter or maybe it's Cobalt Strike or something like that. But the static, you can do a lot of different ways. You can actually stretch the binary. You can introduce different entropy in the binary. And so that static gets deployed there. But the problem is it does only one thing, right? if you deploy that bundle in a static scenario, you have detonation dependencies. Python is not there, some compiler is not there, maybe the libc is even augmented with something else. We don't know, right? We can't really build static environment, static payload outside of the company, or we couldn't in this case, and make sure it's 100% working on our side. So the environment is the issue too. And then long-haul activation. What do you do with the static thing? You can only do one or two things, right? You need more functionality. That sometimes is an issue. Plus, you can do a lot of dynamic things there as well. And last but not least, and we're going to actually see the reason for it, is the coupling variance. When you compile your static payload, everything is known about it, right? There are no sort of dependency for evaluation of what it does in a lot of ways. That's that was the issue for us. We wanted to do dynamic, but we couldn't do dynamic. We wanted to do static, we couldn't do static. So what do? What if there is some hybrid approach? What if we take the pluses from, for example, dynamic side and apply it to the static or vice versa? So we decided that from the dynamic side, the plus would be the less chance of detection if it's small or somehow abstracted from already known binaries, right? Dynamic is also having more flexibility, but the undesired static traits that we need to remove is the the close coupled loader for the ELF binary. It's a greater size if you want to do everything in one thing, and then it also has more chances of detection because everything is sort of known about the static side. Thinking through why static is out of favor is because of that, all these minuses. Let's match them up together, right? Can we improve static delivery? It seems on the first case it's not possible, right? You either do dynamic or you do static. But can we actually try to solve this issue? Went back to the drawing board, start thinking, what are we doing wrong? We went the static route because dynamic was shut down. The static was the way to go for us. First mistake was, okay, we placed the payload buffer. We placed the payload into a buffer that is in data section, right? So when you compile something, everything is in the data section. You can inspect it, and you can deliver that binary. It's very transparent. So every single attempt that we tried, got picked up by that, linear buffer, and we were done. The other idea was to say, okay, well, if you're going and inspecting the data buffers, are you also going and inspecting the sections? What's in the section, right? In the previous talk, we saw the bind section for eBPF. Similar thing can be done manually with ELF binaries. So you can basically say, here's a code. You can say, okay, we'll place that stack or that buffer with a payload into a specific section, compile it, and then somehow reach to it and retrieve it, right? You can do mem copy from your hosting executable and reach out to the address of your buffer in a different section, retrieve it, and you're go, right? That did not work. Another thing we tried was, all right, well, if you're not doing it on a compiler level, maybe something to do with the compiler, let's go down to assembly and basically say, okay, well, take the binary, the payload, let's just say Metasploit, right? Stuff it into a section, but do it through the binary inclusion. So should accomplish the same way, only you do not have the linking through the compiler. You just have a direct placement there. Retrieval and code is very similar to previously. You find a memory location and you go. All right, that did not work. Okay, so all right, let's go deeper into assembly. Let's just write everything out. Let's just do inline C code with assembly. Let's just define the section with proc bits that it needs to get into the memory, load it into the memory. And we used a package from a different open source package to do that, to try to do exactly the same thing. Basically, we're trying to find out what kills us. We have no way of knowing. We do not have access to the EDR console. We do not have any feedback. We just basically get a knock on the, on the door, say, hey guys, you're still here. We already know you're here. All right, so that didn't work. Really going back to the drawing board, starting sourcing the ideas, start looking at the ELF format, start thinking, okay, here's what ELF ELF binary really is: a bunch of sections on a disk, right? That somehow gets into the segments onto the memory. It's not always one-for-one. Some things are loaded, some things are not. Some things are staying on a disk to describe the executable. You can strip it all out. But what really goes on, right? And what we found out is that operating system loader, the ld.so, when it loads the ELF, it doesn't actually load all the sections into the memory, right? It's governed by the flags called pt-load, right? You basically say, okay, I want this section to be loaded into the memory because it contains something useful. Compiler abstracts all of it from you, right? But since we need to do more, we say, all right, well, why don't we take advantage of that trait that operating system doesn't always load all the sections? Okay, a real issue upon multitude of hours of kind of trial and error is that we're betrayed by the compiler. The compiler actually is not our friend because we do not control what it places into the binary. We do not control how it links all the sections, and we do not control how the loader, ld.so, will see the binary. Compiler does its own thing. It needs to get our program loaded, right? And that's its main purpose. But it's not our friend, okay? So let's go through the ways of how it's not our friend. We already mentioned that pt-load is not our friend because once it's in memory, it gets inspected, right? The way EDR works on the unwrap, it kind of goes through the memory and says, okay, I see some interesting things, even though you've modified the flags on the section, read, write, execute, you remove the write and execute, then you added one. I still detect you. All right, fine. What do? Forgo the compiler, forgo the linking. But then the question becomes, how do we construct this binary? Okay, the path to constructing such binary, the answer to that, or at least the hint, was right there, right? Because the operating system loader does not load all the sections. What are the sections and what types of the sections that it doesn't load? And one of it is SHT node, for example, right? It's something that every executable on Linux, well, almost every executable on Linux has. It just basically has a structure where it says, all right, it was compiled in such a way. Here's the ABI version, maybe some licensing version, things like this. Something that is being used by the compiler, but not necessarily part of the execution itself. Okay, so let's go with that. Here we basically say, all right, well, not only that it doesn't load into the memory directly, but it has a very convenient structure of records. Structure of records means we can actually do multiple payloads. We can store multiple disparate addressable kind of bins of data in it. That's useful. Maybe we can implement something that will help with what we're trying to do. Okay? So if the compiler is not our friend, then how do we make sure we can actually decouple the payload from the executable itself? So far, the ideas are to create a dormant section in an ELF image. It's dormant. It's not loaded, right? It doesn't have proc bits. It doesn't have pt-load in it. It's just sitting there. It's dormant. Don't load it in memory by the operating system loader. Check. But then, how do we find it? How do we address it, right? The plus side is that we've decoupled where the payload lives from the actual loader, but it needs to talk to it somehow. Okay, and the issue is if we compile it, there's going to be still tight coupling of the memory address to the section, to the payload, or a set of payloads. Okay, so what we do, we basically say, all right, let's run with it. Let's stuff our payload into a node section, leave it be. We'll solve the next step later. So we now want to create an ELF section that is outside of the loader. Loader cannot be operating system loader. It has to be our loader that basically says, go to this section, find it, load it up, and do whatever you want. Okay? How do we do this? You don't have any tools. I mean, you do have tools in your lab. You do have tools on the red side, but you don't have any tools on the blue side. How do you actually instrument that? Well, if we go back to the structure of the ELF, every section is delineated, right, by a memory address. There's a map that basically says that's where it starts, here's the size of it, and you can calculate where it ends. The offsets can be calculated directly if you have a map of it, okay? So why not have an agnostic binary, the loader, have a section somewhere in its own binary, somewhere else in the binary, and you basically attach it at the binary level, not the API, but basically at the offset, right? We teach the loader how to find and load its foreign data section. It doesn't know anything about it. It knows how to load it, but it doesn't know anything about where it's loading it from. So this is the docking part where you basically say, hey, loader, you binary, hey, the section that is a standalone section with a payload, just attached to itself. It's sort of like a virus, if you want to call it that way, but we'll see how it's actually done. Okay, so what are the advantages of the compiler is the problem, and we need to decouple the payloads, and yet we also need to avoid the operating system loader. So now, if we're compiling code into a section, not attached to the executable, compiling a loader, a standalone executable, and then we're gaining not only separation of two binaries, but we also executing the loader without knowledge of what it's going to be executing. So if loader appears on the system and defense picks it up, all it is just basically a pointer to something it needs to load, but it doesn't have any trace to what it's loading, right? So it's kind of dynamic, but it's really static because we are not reaching anywhere else. We're not using other executables. We are basically using the section, but the loader doesn't know anything about the section except for where to find it, right? Okay, so that gives us a really, really good sort of pointer into not using the API, which is available through the compiler, but use the ABI, the binary interface that works inside of the ELF at the binary section level. It's a little complex, but we'll go through the details and demo for sure. I would like to just point out at the bottom of it where it says the C is the C code. So we're not moving. We're moving from C code into something that is basically. Oops, too far. Okay, so on the bottom, we are not compiling C code. We're basically attaching the binary. That's our hybrid unit of payload carrying capacity, okay? Okay, what is binary compatibility at section level? We have the injector, we have the loader, and we have somewhere a section. A section can be attached to the loader itself, right? But the loader doesn't know anything about it, it just knows that it needs to go somewhere on the disk and lifts it up. Right? So we start looking at the system where the system is split in between creating a loader, creating a payload, and delivering it all in one executable, but the sections do not know about each other. What do we get? Static ELF loader, it's standalone, it doesn't have payloads. It has generic mechanisms to load sections on demand and bootstrap the payload from it. The key understanding here is the ELF loader doesn't know anything about what it does. It doesn't need to change what it has. It doesn't need to change any permissions on the memory section. It doesn't need to manage any kind of dependency through the code. All it needs to do is say, okay, somewhere in my binary, somewhere, I'm going to go and load something, and then I'm going to give it to somebody else. That somebody else is coming as a later stage. But so far, we have this static loader that is agnostic to the payload. The sectional payload, the payload is inside of that section, is created separately in the lab or on the red side. It can also be created at the company side, provided there is a compiler, but we're not taking this into account here. Then the sectional payload is docked to the loader itself at the binary level, not a compilation level, and it can be redocked, right? If you have another payload, you take one out, place another one in. So you achieve better dormancy control. What if you deploy something and then you need to stay dormant for a month, right? You basically can have a table of contents for different payloads, when they need to trigger and how they need to trigger. And you don't need to use the dynamic fetch from the network. Another thing that we needed to fix, remember we talked about the packed executables. We needed to bring in packet because it had the tools that we needed. However, frozen binaries are almost impossible to work with because of the dependencies if you need to achieve a little bit more than just default run, right? So by making multiple sections with payloads or stuffing multiple payloads in that SHT node records, we can have packing without using UPX, for example, without using any kind of compression, and without creating the temporary files when you're actually trying to go and find that sectional payload. So docking allows us to do that sort of alternative way of kind of packing multiple executables into one image. And no overhead, right? You don't need to do any kind of compression on it. In-memory options, we'll talk about in-memory options that it gets us. And really, it still is a correct ELF executable. It runs, it does what it needs to do, and we're basically solving our multiple problems here. Here's the kicker, here's the injector bonus. The injector that has this section in it, what's it to say that I cannot have two injectors on the system, and one injector can take section from another binary and run it? So EDR cannot trace that kind of stuff. You cannot, our job as Red Team is to break the dependency of the flow of detection, right? And this is one way of doing it by saying, all right, not only I'm allowed to find my own section loaded up and there's no trace of what I'm doing, but I can actually find another executable that somebody else brought in, grab section out of it and do the same thing. So now you're actually multiprocessing, right? You're doing, or yeah, your EDR needs to trace multiple processes to be able to see what people are doing. Actually, not even the process is a static file in a disk. Okay, all that culminates into ELFPack factory, right? Some of it is done on the red side, some of it is done on the blue side. We're using injectors freely. We're marrying key sections to different injectors, and we basically deploy this whole cake to that hardened host and say, eat it, all right? Go try to detect that, go through your BPF controls, go see what I'm doing. The BPF challenge and BPF fight is going to come next slide, but essentially we split it into various things, but they kind of work together. Okay, the last issue is the fileless execution in-memory unwrap, okay? Now, nobody tells us how the EDR works there, right? We somehow need to figure that out, and one of the reasons we were failing once we got everything on it was because the launch itself was was detected, right? First, we went with option B, which is the syslin-mfd create. It's a very, I mean, it's widely known as being used for fileless execution, but what's a poor man to do, right? Poor man needs to try. So we tried that. We did this with libreflect. We essentially said, okay, here's the loader, go find your section, and then load it up into the memory directly. Got detected. They said, okay, guys, you can't do anything else. Here's your memfd trace from BPF, right? Here's your log. Okay, so the real issue came with execve. Execve is this system call that allows ELF binaries or executables on Linux to actually exist as a process. Launch it up. Whether you are the loader or the system is the loader, you still need to call it exec so you can actually build the process and launch it up. So our last job was to do away, kill the execve. How do we do this? Well, we went with option A, which is the userland exec, right? In the Windows, it can be thought of as a process hollowing, right, where you overlay your image on top of the running process, and then you basically become somebody else, or they become you. So userland exec is a really good thing. It only is used for one specific issue, to overlay your own image with somebody else and go do things. There are trade-offs and downside for both. Obviously, syslin-mfd create is a lot more detectable, right? But userland exec only gives you one shot, right? You can't spawn other processes because you essentially overlaid yourself. You can't go back. You can revert. Any error in your code kills you. But we took a shot, right? We took a shot, and by the way, and you can't daemonize itself when it launches. So for long persistence, you have to use other things to become a daemon if you want to, but for our intents and purposes, userland exec worked. We'll see how it gets detected and how it doesn't get detected. So the static side, what the defense saw, the top part of the slide is we've taken MSF metal, which is the Linux payload for Metasploit, and give it to the blue team. They said, okay, well, here's the bin walk. You're completely matching towards our known signature. You're failing, right? The section payload done with ELFPack on the same MSF metal shows you that much. And the last, I don't know if you can see well, but the last two lines on that is only my debugging to know that I'm actually running and to show the blue team that it's actually an executable, right? So essentially, all you're seeing is minimization of the signature between, for the static side to detect either the verbatim metal that gets deployed versus the ELFPacked one. And the other thing, the dynamic side, the defense also was not sleeping on the dynamic side. So they've created signatures for us, right? And standalone payload for metal gives a signature that is quite different from a section payload. So you take the same metal and you ELFPack it, turn it into section, trace it all, however you need to do it, and you deploy it. And if they rely on behavior, which not a lot of EDRs do, but let's say they do, they still have a different match, right? So that was a win for us. Okay, and then you also have kind of description of first after the engagement we've created a signatures for the ELFPack, gave it to the defenders, so now they can actually do signatures on that. But then we, in turn, also found out how they were doing the filtering. They took sysenter memfd open and obviously, or enter and exit for memfd. That's how we got killed on version B, right, on the memfd create. And they also tracked every single sysexec, like every single thing that gets executed on this host was essentially tracked. So we solved the exec, we solved the delivery, we solved the bypass for BPF, we've solved linking, right? What else? Let's take a look at what we did. Okay, I'm going to try to walk through. The screen is a little busy, right? But essentially is divided into, just for the demo purposes, divided into multiple screens. You see the victim machine. You've got the Metasploit payload server listening on the background somewhere. And you've got a couple of screens for BPF and Yara rules, right? How they detect. And then the triage code that needs to detect it. And let's just go through that. So on the bottom, we're basically running that whole factory for pre-built ELFPacking. And the argument to it is we did some other things, like we XORed the payload, we XORed the records in SHD node, we gave it a key just to be sure and safe. So that's what we're going to do here. Okay, so that's the payload server. We don't have any sessions. Hopefully we get sessions. So let's go over the loading. So we have the ELFPack, the packer that takes the loader, agnostic to what its payload is, right? And then it takes the metal binary. Out of all this, it creates a cradle, or first stage, however you want to call it, right? That's the thing that gets deployed to the victim machine here. Okay. Then what we're doing, we're sticking it into a buffer which mimics what a lot of Linux systems have. They have this node GNU buff where they have the description of the ABI, maybe licensing, libc things. Usually it's not very big, but we make it big by sticking things in it. We are instructing it which type of section is going to be, right? And then something that we did on top of it, it's the XORing, and then we gave it a key, right? Pretty straightforward, just for static analysis. Okay, and then we have, so in this factory, we have options to either do memfd, or do user exec, or maybe do daemonization, backgrounding, whatever the case may be, and also passing arguments to our payload. Let's say metal can have its own arguments that it kind of needs to work with. So anyway, this is all kind of part of that factory that's working. Some of it is done in the lab, but just for the sake of time, we kind of did it in one place. Okay, so let's load and bootstrap the implant. We've launched it with memfd, right? We're going to see the detection for it. First, the callback, of course. Everybody likes to see a session. All right, we got the session on it. Make sure that it's working. It's working, meaning that it's a viable ELF. So, kind of is. Gives you the process table, and then we're going back and try to relaunch with user exec. Let's see what it does next. Okay, so for detection, I want to show you the code that they've used for BPF, or eBPF in this case, right? It's a description file where they say, all right, every time you see sysenter exec, or you see sysenter memfd create, alert on it. This is a trivial rule, but essentially the EDR builds on it and then does something else with it. But detection part is what they've used as a contrived example here, right? So that's what has been killing us here. Now we're deploying this BPF trace. So we're taking rules and we're saying, all right, we're going to act as an EDR, attaching 5 pros, five things that it needs to do, relaunching our thing with user exec. Okay. Going back to the thing, and what we see is that the execution of things to build it, right? We're just showing this as an example. This will never happen on the victim side, but it will just happen in the lab. Is that ELFPack, loader, stager, and where it needs to do. And this is the execution of the actual cradle. And the only system call that it has is the host name. The host name is coming from Metal because it needs to go out and grab something, right? So essentially, no exec, no memfd enter, just a basic host name. And even if you recompile Metal, you can probably stick an IP in it and it will never call that, okay? So was clean for us from that perspective, right? No detection on it. We were able to do it on the host with no compilers, no interpreters, heavy tracing of our activities. Yeah, and again, it's a viable session. We're looking at it. And for those who are interested, we're just showing you the Yara rules. You can actually take the Yara rules and start detecting that sort of technique, right? You basically say, okay, well, maybe I can inspect the section, and maybe if it's larger than X bytes, maybe there's a payload in it, right? Because SHT node should never have any data. It's very rare that it does, but here it is, right? So you can productize it if you write your EDR, and you can use that. It kind of shows the size of it, the content of it. And last but not least, Yara rules for detection of this doesn't work right off the bat. You can't use config file. You have to write code for Yara to do this because it reaches inside of the ELF section and it actually does some heuristics on it. So that code is also posted on GitHub. You're welcome to take it, and if you run your custom detection, then you can do that. All right. So what are the takeaways? Aside from the fact that we were successful finally, right? We got our little presence in the Bastion host, the jump host, and we were able to go out to the entire space of Linux and get good things for the customer, right? But the real thing is that you can create a hybrid approach between static and dynamic by using section as a unit of payload, right? You can high payload in sections. You can actually make section loader agnostic from the actual payload, right? And thereby you break the kind of rules of how tracing it happens, right? There are no memory addresses to go by. Basically reads its own image, finds an offset, reads off of it. Then you forego the API completely. You work on the ABI level. Your section gets binary attached to its own loader if you want to. And then you can also overcome the limitation of packers, right? You don't need to do compression. You don't need to do temporary file systems. You don't need to do any of that. All you have to do is basically create a roster of payloads in your sections and notify the loader what to load and then how to load, whether using user exec or using the memfd if you so choose. For those of you who are on the defensive side, we provided you with Yara rules, how we would kind of detect that. Obviously, you can critically look at it and say, hey, that needs to be improved, of course. But it's a race, right? You will be able to detect, will be able to overcome. And then deeper packing, encryption is all going to be in the product version of it, obviously, right? Because things are moving forward. Last but not least, now you can use factories to borrow sections from different executables on disk, and you should be able to solve for that issue as well. The code is on GitHub. You can access it and play with it, modify it. It's MIT. You know, it's free for all. We don't have any rights for it. We just developed it for you guys, for our needs, and hopefully it'll be useful for you. And with that, I want to say thank you, gracias. And if you have any questions, I'm here to answer them.